This presentation is entitled Data Privacy, Security, and Consent. In this presentation, we look at clever use of ontologies to determine who can see your data and what data they're allowed to access. Data privacy, security, and consent management. In order to deliver the Holy Grail, a number of information technology challenges must first be met. First of all, there is the notion of accessibility. It turns out much data today is still in paper form. A second challenge, disparity. Information today oftentimes resides in what are called silos. A third challenge, computability. Much data today is still in an unstructured form. A fourth challenge, queryability. If you have structured data, the technology today is such that it is very difficult to navigate complex structures. Another challenge, one of fragility. Oftentimes in an enterprise system, whenever you make changes to one layer of the architecture, you oftentimes get this ripple effect where other layers break. Another challenge, one of rigidity. The inability to easily change data schemes on the fly. Another challenge, one of complexity. Oftentimes, enterprise systems today are comprised of potentially tens of thousands of underlying database tables. In order to query such data, you actually have to know the names of those potentially tens of thousands of tables. Another challenge is one of evolvability. Let's say you have a legacy system and you want to introduce a new system into your enterprise. The challenge is migrating the data from your complex legacy system to your new system. Another challenge is one of interoperability. Today, interoperability is restricted to standard message exchanges. And lastly, one of expressibility. The challenge today, in order to do queries on structured data, you have to have IT skills. This technology called TC-SQL is a new kind of technology featuring the following capabilities. First of all, it features the ability to do graph management. In particular, the maintenance of this thing called transitive closure. It features the notion of something called soft schema, which provides the ability to support object-oriented programming directly in a relational database system, complete with notions of classes and objects and single and multiple inheritance and polymorphism, and a collection of other capabilities on top of these two basic capabilities. We're going to start by doing a little graph theory here. In front of us are two graphs, a family tree and a graph of bus routes. Some of the components of a graph consist of the following: the notion of something called nodes. In this family tree graph, the nodes happen to be the names of people here. A second component of graphs are these things called connections here, or edges. And they happen to be the arrows we see between nodes here. Sometimes in graphs, you have a semantic relationship associated with these arrows. In this family tree graph, we have a father of relationship, and we have a mother of relationship. Sometimes with graphs, you have scalar values associated with the connections. In this bus routes example, the scalar value represents a cost of going from one city to another. The notion of transitive closure is a concept that is foreign to most people. So let's look at a definition of transitive closure. Given a graph G, the transitive closure of a graph is the set of all potential paths between all nodes in the graph here. So in fact, the transitive closure of a graph can be represented using a relational table here. So the way to think of the population of this table, you can think of it as follows. Take any two nodes in the graph, let's say starting with N1 and looking at N6. Does there exist a path, directed path from N1 to N6? The answer is yes. Therefore, we see a transitive closure record here. Does there exist a directed path from N2 to N6? Notice I say the word directed, you got to follow the directions of the arrows. The answer is no. So N2, N6 does not show up here. So what can you do with the transitive closure of a graph? You can use it to navigate a graph. So if we want to know all of the descendants of N1, what we can do is write a select statement as follows. Select child from transitive closure where parent equal N1. Now let's play computer a second here and let's execute this query here. Let's find all the rows here where the parent has a value of n1. We see that in green here. And let's find all of the children from all those records. And what we find is we get n2, n3, n4, and 5, n6. So in fact, that represents all of the descendants of n1 here. Now, one of the unique things about transitive closure with respect to TC-SQL, TC-SQL features the ability to maintain transitive closure in a graph as a graph changes. So normally, if you're adding or deleting nodes or connections in the graph, what happens is you typically have to rederive the transitive closure from scratch. One of the features of TC-SQL is its ability to maintain transitive closure whenever nodes or connections are added or deleted from a graph. The notion of transitive closure is a concept that is foreign to most people. So let's look at a definition of transitive closure. Given a graph G, the transitive closure of a graph is the set of all potential paths between all nodes in the graph here. So in fact, the transitive closure of a graph can be represented using a relational table here. So the way to think of the population of this table, you can think of it as follows. Take any two nodes in the graph, let's say starting with n1 and looking at n6. Does there exist a path, directed path from n1 to n6? The answer is yes. Therefore, we see a transitive closure record here. Does there exist a directed path from n2 to n6? Notice I say the word directed, you got to follow the directions of the arrows. The answer is no. So n2, n6 does not show up here. So what can you do with the transitive closure of a graph? You can use it to navigate a graph. So if we want to know all of the descendants of n1, what we can do is write a select statement as follows. Select child from transitive closure where parent equal n1. Now let's play computer a second here and let's execute this query here. Let's find all the rows here where the parent has a value of n1. We see that in green here. And let's find all of the children from all those records. And what we find is we get n2, n3, n4, and 5, n6. So in fact, that represents all of the descendants of n1 here. Now, one of the unique things about transitive closure with respect to TC-SQL, TC-SQL features the ability to maintain transitive closure in a graph as a graph changes. So normally, if you're adding or deleting nodes or connections in the graph, what happens is you typically have to rederive the transitive closure from scratch. One of the features of TC-SQL is its ability to maintain transitive closure whenever nodes or connections are added or deleted from a graph. Let's look at the difference between data versus information versus knowledge. If I showed you the following, would you consider this to be data or information or knowledge? Well, it turns out it's just data. And the reason why is because you look at this and it looks like a column of names. That's because it is something you recognize. This looks like a column of diseases. That's because you're familiar with it. But by itself, it is merely data, just text strings. Now, if I add column headers here, these column headers are what are known as metadata. And so what we get is data here plus metadata is our definition of information. Well, what if I take and put an overlay here, the following. We see type 1 and type 2 diabetes are specializations of this more general category of diabetes. Ulcerative colitis and Crohn's disease are specializations of this more general category called digestive diseases. So what do you call this structure here, this knowledge overlay? I call it meta-information. And so my definition of knowledge is information plus meta-information. This knowledge overlay here is something called an ontology here. There are semantic relationships between the nodes here. And what this allows you to do is the following. If you view this as a relational table here, you can certainly ask questions about who has type 1 diabetes in your database here. What an ontology overlay allows you to do is ask higher level questions. Tell me all the people in my system that have diabetes in general or have autoimmune diseases in general. The object-oriented paradigm can be represented as a graph problem. So here we have a class here called class 1. which has properties A, B, and C, and a hazard relationship between the class definition and its associated properties. We also have another class here called class 1.1 with properties D and E. And we see a relationship here between these two nodes, an is-a relationship, meaning that class 1.1 is a specialization of class 1. Now let's look at a graph here. Let's look at what happens if we want to instantiate class 1.1. Let's look at the equivalent object graph. In this case, it would look like the following. Assuming we want to instantiate class 1.1 and we're going to call that object 1, what happens is the following. We first want to instantiate properties D and E, and then we want to look at this inheritance is a link here to inherit properties A, B, and C, which is what you see down here. Okay, now let's look at the relational tables needed to support this paradigm here. So we have the notion of a class table here, which represents the nodes of our class graph here. It's basically a name-value pair here, and we have a type column here, and legal type values. This represents basic class types here. We have a class connection table of parent-child nodes here and a connection type here. In this case, it's going to be either has-a or is-a. And then we have a transitive closure table representing the transitive closure of this class graph. And assume for a minute that this transitive closure table is automatically populated and managed whenever nodes or connections are added or deleted in this class graph. Let's look at the tables needed to support our object graph here. We have a table called object, which represents the nodes of our object graph here. Again, it is basically a name-value pair with a class column here representing the kind of class that we're instantiating here, including the class properties. We also have an object connection table here, which represents the connections of our object graph. So it's a parent-child pair, again with connection type. And we have a transitive closure table associated with our object graph. And assume here also that this transitive closure table is maintained automatically whenever nodes or connections are added or deleted in our object graph here. So this whole paradigm here I'm describing here with these 6 relational database tables is something known as a soft schema. In the last slide, we looked at the notion of something called a soft schema and the 6 relational database tables associated with it. In this slide, we're going to look at a query which utilizes a soft schema and does a join to conventional relational tables like you see here. In this example, we're going to do the following query. Find all diabetes patients here. So at the top here, we have a graph, something called an ontology, where you have a semantic relationship between nodes here. In this case, it's an is-a relationship here. At the bottom, we have a standard relational table, an electronic healthcare record table here with patient information. And so the query looks like the following select statement here. And what we're going to do is we're going to play computer and run through step by step what happens in executing this query. In the first part here, we have a where transitive closure patient is diabetes. So we show that here. And what we're going to do is look at all of the children, in other words, all the descendants in the transitive closure table here. So that shows up in purple here, all the descendants of diabetes. And then what we're going to do is a join on the electronic healthcare record table here, where the fact value corresponds to the descendant value here of the transitive closure. And then we're going to return here the select e.patient. We're going to return the patient column information here in the result here. Now this query is an example of a query type called a subsumption query. Having looked at some powerful TC/SQL-based technology, let's look at how to apply that technology to a particular problem. How to manage privacy, security, and consent of data. So we're going to consider the following solution, which consists of looking at 4 kinds of ontologies. First of all, we're going to look at domain ontologies. For example, in the area of healthcare, there's a system called UMLS. We're going to look at personnel data. Again, the example being healthcare. There are healthcare documents called HITSP C32 documents containing patient data. We're going to look at social networks, for example, a hierarchical classification of family and friends. And we're going to look at domain professional classifications, for example, hierarchical classification of healthcare professionals. We're going to look at defining data sets containing terms from these first two ontologies here. And we're going to look at defining requester sets consisting of members from these two ontologies here. And we're going to look at defining policies that associate data sets here with requester sets. And last, we're going to look at how to enforce policies on all personal data queries. To illustrate the concepts described on the previous slide, we're going to use healthcare examples. So we're going to be looking at four kinds of ontologies here. This first kind here, the domain-specific kind of ontologies, we're going to look at a system called UMLS, which has a number of different ontologies here. These ontologies have every kind of vocabulary term you can imagine related to healthcare. So it's every kind of disease you can imagine, every kind of body part you can imagine, every kind of drug you can imagine. Concerning personal data, we're going to look at a healthcare document called a HITSP C32 for a patient named Fred Mann here. This is basically an XML document broken down into a number of subsections here. At the bottom here, we see a relational database table that has the patient here, Fred Mann, and the different facts found in this XML document here. Let's look at a social network defined by Fred Mann here. So Fred has created this social network divided into family members, friends, professionals, further subdivided into other categories here, and assume for each of these categories here is a list of people. At the bottom here, we have a relational table that reflects exactly that. So we have a number of people here, and here's the bucket or the classification that that person resides in. Here is a hierarchical classification of healthcare professionals here. So you have general practitioners, internal medicine, so on and so forth. Assume here also that each of these categories has a list of healthcare professionals. So we see a relational table at the bottom here of exactly that. We have a name of a doctor here and a particular classification bucket they reside in. Here is a hierarchical classification of healthcare professionals here. So you have general practitioners, internal medicine, so on and so forth. Assume here also that each of these categories has a list of healthcare professionals. So we see a relational table at the bottom here of exactly that. We have a name of a doctor here and a particular classification bucket they reside in. Let's now look at some data set definitions created by Mr. Fred Mann here. He created 4 data sets here, and each data set is a comma-separated list of categories of data pertaining to Mr. Fred Mann. Let's now look at some requester set definitions created by Mr. Mann. He created 3 requester sets here. Each requester set is a comma-separated list of categorizations of requesters here. So we see endocrinology, we see doctor, family members, sports friends. Let's look at some policy definitions created by Mr. Mann. Here are the data sets he created, and here are the requester sets he created. And the policies he defined are the following here. So here's Mr. Mann, and for data set 1, he is saying requester set 1 applies to that data set. So all of the members of requester set 1 have access to the data defined in data set 1. Similarly for data sets 2, 3, and 4. So you get the idea here. Let's look at how to enforce the policies defined by Mr. Mann. We're going to assume here that all of the healthcare information pertaining to Mr. Mann resides in a soft star schema data warehouse, the kind that we talked about in earlier slides. So we can assume the following here. Assume that we can do a select statement here from a view called fact, and we can pass in the name of the requester and the name of the patient. In this case, it is Mr. Fred Mann. And imagine we have a set of requesters here, a Dr. Vasa, who happens to be an endocrinologist, Dr. Singh's a primary care physician, Mr. L. Lewis is a fishing buddy. So each of these people potentially wants to know information, healthcare information about Mr. Mann. You can imagine what's returned is a list of healthcare information that abide by the policy definitions according to those captured and specified by Mr. Mann here. So not everything, not all healthcare information about Mr. Mann is returned, only that information that is allowed. So what have we learned from this? Why is this valuable? Well, first of all, what I've shown you allows for ontological classification of requesters and ontological classification of requested data. And lastly, the policies demonstrate a very powerful yet simple way of filtering structured and unstructured data at any level of granularity.